Today I will talk to you about the changes that the advertising industry is facing. The cookie in the title, as you might expect, refers to third-party cookies that are soon going to be phased out by all the major browsers. And the reason this talk might be interesting to you is that historically, real-time bidding industry has been very high-tech and is employing a lot of machine learning solutions. As these changes happen and as we switch to a new environment, we will have to find new ways of thinking about our models, of designing them, of optimizing them, and of deploying them to production. So I hope this talk is going to be interesting to you. Feel free to post any remarks or questions that you might have live in the chat. I can see the chat on my second monitor, so if there is anything you'd like to ask about during the presentation, please feel free. So a very high-level plan for today. As I mentioned, there is a lot of interesting challenges before us, and one of them is the problem of federated learning. I'd be actually very curious to hear how many of you are already familiar with this concept, with federated learning, or with the problem setting in general. I'm wondering how to hold a quick survey. Perhaps if you know what federated learning is, you can just write yes in the chat window or no. I'll be very curious to see how popular this branch of research is amongst our audience today. I think there's some latency between our stream and the chat that I'm observing, but I see a couple of answers already trickling in, and the negative answers seem to be more popular. So I'm happy that some of you will learn something new today, and perhaps for those of you who already know what federated learning is, you can refresh a couple of concepts, and we can make sure that we focus on the same definition. So I'll start with a high-level overview of federated learning, and then I'll move on to real-time bidding. I'll introduce real-time bidding in very high-level terms as well, and I'll explain how the federated learning setting is now becoming relevant for us. And this will bring me to the description of a number of challenges that we are facing as an industry and that RTB House in particular is now very busily solving. So before we move on to the main point of the presentation, let me say a couple of words about myself. My name is Jonasz Pamuła. I finished Jagiellonian University in Kraków. During my studies, I was mostly focusing on algorithms, and I was very keen on participating in competitive programming competitions. During my time at Jagiellonian University, I had 2 internships at Facebook, and later on I moved to Zurich, where I worked for Google, first on YouTube and then on search quality. Since 2019, I'm at RTB House, where I now lead the research team. And many of the topics that I'm going to be describing today are the focus of our attention in the past months or even past years, and certainly for the upcoming time. A couple of words about RTB House. Some of you might know us from a previous edition of ML in PL, In 2019, we led a workshop on recommendation systems. We are also preparing a course for for Warsaw University in the coming summer semester. We are going to lead a course on distributed systems. For those of you who don't know us, RTB House is a Polish company founded in Warsaw in 2012. We are providing retargeting services globally. We work with around more than 3,000 advertisers throughout the world, ranging from small companies to leading e-commerce platforms. So we serve ads for companies like Adidas, Orange, Decathlon, Trivago, and more. And I think what is interesting about RTB House from the perspective of this conference is that we consider ourselves a performance-oriented advertising provider. What that means is we have an IT department of around 100 engineers. The research team consists of 15 researchers and engineers, and we take our research very seriously. Any improvements that we make to our bidding system or to the models that we develop is immediately seen in companies' core metrics like revenue. Just to give you a little bit sense about our scale, at peak we handle more than 10 million queries per second. And each such query involves the evaluation of a number of different models, neural nets, and other kinds of models. So basically, we're working with lots of computing power, lots of data, and lots of interesting research problems. But let's move on to the main point of today's presentation, which is the changes in real-time bidding industry. One of them is federated learning, how federated learning is now going to be applied in the area of real-time bidding, and what that means exactly for us. So let's start with federated learning. Federated learning is a setting or a concept that was introduced in a 2015 paper coming from University of Edinburgh and Google. The authors of the paper refer to this problem as federated optimization, but I think federated learning is a more widely used and perhaps established name right now, and that's also what I'm going to be using. And to introduce federated learning to you, I am going to use an example that was used by the authors of the very paper that I mentioned. Imagine we are working on a software keyboard, and one of the features in the keyboard is, in order to make the typing experience as convenient as possible, the keyboard will propose a list of words that are potentially the next word that you are going to want to type. I'm sure that everybody knows this kind of feature from practice. Of course, for this feature to be useful, the predictions have to be somewhat accurate. So at least sometimes the keyboard will have to guess what word you have in mind as the next word, and that is going to make the typing experience more convenient. And as you may expect, in order to implement such a feature, we are going to need a language model. So the language model will accept some prefix, a prefix of the type that you have already typed, a prefix of the text that you have already typed, and it will try to predict the next word that you have in mind. And an important assumption about our setting is that there is already a large number of people that are using our keyboard daily. So a large number of people use our keyboard to type some text regularly. Some of them do that more frequently, some of them do that less frequently. But a very sensible approach to developing our model would now, of course, be to try to gather some samples or perhaps all text snippets that people write, assemble all these text snippets in some central server, and in this way form a centralized database that could then be used to optimize our language model. This seems like a sensible approach, though the authors of the paper mention two aspects that could be improved. First, there is certain networking costs that will have to be incurred in order to gather all the text snippets in a central server. Perhaps this could be optimized in some way. And second, there is the privacy aspect. And this privacy aspect is actually what's going to be more relevant to us today. And the privacy aspect is really what's driving the changes in the RTB ecosystem. So a sensible question now that we can ask ourselves is how to design this optimization process so that we don't run the risk of the central server ever getting compromised. As you can imagine, even if the provider of the software keyboard and the provider of the central server are well-meaning and are doing their best to protect the data that they keep on the central server, there still is a technical risk of the central server being hacked and the data being leaked. So perhaps there is a way to avoid sending raw data points from the devices to the central server. And if you think about the ways machine learning models are optimized today, sometimes the optimization process and the computing that's being done is being parallelized over multiple machines. So we could seek certain similarities here and try to perform computations locally on each of the smartphones or each of the edge devices and only send the results of those computations to the central server. And of course, the hope here would be that the results of our computations will no longer be sensitive. So this is exactly what we can do. We can try to process the data points that are present on each of the devices locally. If you think of many popular architectures today, for example, neural nets, the local optimization could consist of the adjusting of the model's parameters, which is basically a set of real numbers, and we could send those updated parameters back to the central server, or perhaps send the deltas of the parameters to the central server. And this way, hopefully avoid the problem of leaking sensitive data. This is, of course, a sensible approach. This is the setting of federated learning, and it's worthwhile to stop here for a second and try to summarize all the characteristic aspects of this optimization process. So first, I drew some analogy to the process of distributed optimization, where the goal is to parallelize the computing that has to be carried out over a number of servers. But here, the setting is actually quite different. In distributed optimization, you can think of tens, hundreds, perhaps thousands of machines. Here, in contrast, we are likely to work with millions or even hundreds of millions of edge devices that will collaborate to optimize a single model. What is more, the dataset that we are working with will be split across devices in an uneven manner. So in our example, you can imagine that some users are more active when it comes to using the software keyboard. Some will only type a couple of text snippets a day, and others will type much more. So we have to take into account that some edge devices will contain local data sets consisting of only a couple data points, and some of them will have orders of magnitude more. Not only that, these local data sets will most likely be biased. We have to be prepared. In our example, you can imagine that some users will use very short sentences, perhaps short words and lots of abbreviations if that's their style of communication. And other users will type longer sentences, perhaps with more sophisticated words. So we cannot make the assumption of the data sets being drawn from the same distribution on each of the devices. And the first 3 points describe the nature of our data set, how it is distributed across our edge devices. And another important consideration is the local resource limitations. In distributed optimization setting, we would probably strive for maximally using all the available resources on the device. Here, in contrast, the process of optimizing the model is probably just a side task. It's not the main task that the edge device is supposed to be doing. And in fact, we wouldn't want to use too much resources not to make bad user experience for the users of the smartphones. So we will have to use as little CPU, as little networking as possible. We will also have to account for the fact that some of the devices might not be available in the network all the time. In fact, the authors of the paper mentioned that it might be a sensible approach to gather the data points on the device and process them in batch when the device is plugged into charging and is connected to a high bandwidth Wi-Fi network. So these are all important characteristics of our setting, and still our goal is to learn a single high-quality model. This is a very high-level description of the federated learning setting, and the specific approach to optimization or to learning that we can take in this setting will heavily depend on the particular characteristics of the task at hand. As you will see, federated learning applied to RTB will have certain specific differences compared to the example with software keyboard and smartphones. And also the kind of model that we are going to be optimizing is going to be different from the language model that I mentioned in my original example. And the example, of course, comes from the paper that I mentioned at the beginning. So before we move to the setting of real-time bidding, let me quote one sentence that the authors wrote in final remarks in their paper. The authors predicted that the setting of federated optimization will be increasingly important for practical application as privacy issues get ever more pressing. And as you will see, this prediction is proving true right now in RTB ecosystem. And now I'd like to tell you how this federated learning is going to be applied in the setting of RTB. So of course, before I say or before I describe how federated learning is now going to work, it is probably good to introduce what real-time bidding even is. Not many of you, or not all of you, might be already familiar with what RTB does. Imagine there is a website that wants to optimize or that wants to monetize their efforts through the showing of ads. And of course, if the website is monetizing their operations through ads, it is probably a good idea to try to find a way of doing that that brings as much revenue as possible. And to that end, the website might opt into RTB. In practice, what it means is that when a user visits our example newsite.com, the web page is going to contain a designated slot where an advertisement may appear, and a real-time auction is going to be held where a number of buyers are going to get a request saying, hey, here's a user that visited our website. Would you want to show an ad? And if so, how much are you willing to pay for the possibility of displaying an ad in this particular context to this particular user? So a buyer, you can think of each buyer as ad tech company that is representing perhaps many advertisers. RTB House is an example of such a buyer. And as mentioned at the beginning, we represent around 3,000 different companies or different advertisers. So after receiving such a request, one of the questions that such a buyer will have to consider is, what ad should I choose? I am representing a high number of advertisers. Which ad should I pick and return as my response to newsite.com? And in answering this question, there is a number of sub-problems that the buyer may consider and that the buyer, in fact, will consider. One of them is, if I show this particular ad, what is the chance that the user will click it? This is sometimes referred to as CTR, or click-through rate problem. And to solve it, various approaches can be taken. But one sensible approach is to maintain and optimize a model, perhaps a neural net, that will accept certain signals relating to the context and to the user, and will output the prediction or output the probability that the user will click the ad. And of course, CTR is one example of a subproblem that the buyer will consider. Another example would be a model that predicts if the user clicks the ad, what are the chances that they will buy something on the advertiser's page? Or if the user clicks the ad, what is the expected amount of money that the user will spend on the advertiser's page? So there is going to be an array of sophisticated machine learning models that solve various sub-problems relating to the real-time auction. And the predictions or the outputs of these models will then be used to estimate the final value, that is, the price that the buyer is willing to pay for the impression of an ad. So after handling such a request, after processing all those sub-problems, the buyer will return a pair, which consists of an ad and a price. And of course, all the remaining buyers will do something similar and return their proposed ads and prices they are willing to pay for the showing of their ads. Usually the highest bidding buyer wins, the highest price wins, and the corresponding ad is shown to the user. So this is a highly simplified overview of the way real-time bidding ecosystem operates today. And this picture is about to change quite dramatically. Similarly to our example with smartphones, the browser might decide that it would be better for the privacy of the user if the signals required for the conducting of the auction are not sent to external servers. And if possible, it would be better to keep all those signals local to the browser, perform any relevant computations locally, and this way there would be no technical risk of ever leaking any sensitive information. So a very straightforward way of trying to adjust the current ecosystem to performing all the computations locally would look like this. We take all the buyers, and instead of contacting their servers with a request, let's now ask them to provide a JavaScript file or JavaScript code that will perform all the computations necessary in an sandboxed environment locally on the browser. So in the previous slide, you saw that buyer one was operating a server that received request containing all the signals, and now buyer one will deploy a JavaScript file to the browser, and this JavaScript will now be responsible for carrying out all the computations that previously happened on the server. So such a JavaScript module will now try to answer the question, what ad should I choose? What are the chances the user will click the ad if I choose this particular ad? What are the chances that the user will buy something if they click the ad, and so on? And finally, using the predictions coming from all those sub-problems, what is the price that I should propose for the displaying of this particular ad? So the local JavaScript bidding function, or the local JavaScript module, will now carry out all those computations, and this includes the evaluation of all the machine learning models that were previously executed on the server. And of course, there may be many technical questions that are now popping in your mind. How to assemble all the signals necessary for each buyer on the browser, how to make sure that all the ads that the buyer wants to consider are also present in the browser storage. All these are valid questions and not easy questions, but the good answer is that they have already been solved. So there are technical solutions proposed by major browser vendors that describe how to carry out all these operations and finally the auction itself in a completely privacy-friendly way. So we won't focus on the details or the technical details of how this is going to work today. If this is interesting to you, I will point you in the next slides to GitHub repositories, which contain the descriptions of various proposals that solve this exact problem. So how to do it is one question, and another question that that you might be thinking now is such a change even possible? Is it possible to take a very complex ecosystem where many participants maintain advanced server-side solutions along with neural network models and evaluate them entirely server-side? And is it possible to now fit all this to a locally executed, sandboxed in-browser ad auction? And the answer here, in turn, would be it's not only possible, it's already happening. At RTB House, we have an alpha version of exactly such a system. We have tested it end to end. We are able to show ads in this way in Google Chrome. And in fact, entire ecosystem has been very busily working on these solutions for the past 2 years. Many leading participants in the RTB ecosystem have taken part in the discussion and have contributed certain technical proposals of how to go about conducting such an auction. Google Chrome proposed solution named TurtleDove in January 2021, and there has been a hot debate in the industry ever since. There's been many proposals coming from other participants. For example, Microsoft proposed an alternative solution that's named Parakeet. There's been Davki, Parrot, Tern, and many other proposals coming from many companies. RTB House has also been very active in this area, and we have proposed 2 extensions to the originally proposed TurtleDove proposal, which are now going to be incorporated in the final solution or the current iteration of the solution Google Chrome is working on. And this is in fact already being implemented in Google Chrome. I think the bottom line here is that the ecosystem takes these changes very seriously, and this is really happening. This is not just a proposal that's being discussed. So this brings me to the question of how federated learning fits this picture or this new environment for real-time bidding. And this might already be quite obvious to you. In our initial example, we talked about smartphones and language models necessary for software keyboard. And the analogy here is that instead of smartphones, we are going to be working with browser instances, which can run on various edge devices. So the browsers could run on an old laptop, on a tablet, perhaps on a smartphone, or some newer PC. And the model optimization problem that we can focus on is the development and optimization of a CTR model. There is going to be many more optimization problems that we'll have to solve, but for the purpose of this presentation, we can focus on the problem of predicting the probability that the user will click the ad. So a couple of characteristics of our setting of federated learning in the area of real-time bidding. As I mentioned, we are going to deploy our code and our models to web browser instances. Our models, or the code that we deploy, will be evaluated at the time of an RTB auction. And one of the restrictions here is that we will have no ability to maintain state or accumulate data across those auctions. Of course, there will be resource limitations. One of them is a time limit that is traditionally associated with real-time bidding auctions. Most likely, we will have tens of milliseconds or hundreds of milliseconds for all the calculations that we will perform on the device. The time limits themselves are not yet concretely specified. They will be probably specified after first live experiments that are scheduled to happen in the next quarter. Of course, there will be a high diversity of devices where we will deploy our code and our models. So these are all characteristics that we have to take into account when designing our models and designing our bidding system. And last but not least, there will be a very specific reporting mechanism that we will have to use in order to gather statistics from all the browser instances and to optimize our model in a federated learning setting. I will talk a little more about the reporting mechanism that we will use, but what's worth to highlight early on is that there is a concept of privacy budget, which means that there will be a limited amount of information that we can send from a single browser instance, and we will only have access to aggregate data. If we send reports from multiple browser instances, we won't have access to those reports themselves. Rather, we will have access to some aggregates of those reports. So there is a really long list of interesting theoretical and technical challenges that we now face. We won't focus on all of them. Today, I'd like to focus on the machine learning prediction quality, what that means for us and what we are doing to make sure that the quality of our machine learning models and their predictions can be as good as possible. What challenges we face when it comes to reporting, and finally, what challenges we face when it comes to the optimization of our models. Let me just quickly mention 3 other challenges that we will likely have to solve in the upcoming months. One of them is limited computational resources on the browser. And what we'd like to achieve here is to be able to execute as complex and as advanced machine learning models as possible. So we are looking for various technical ways of optimizing the execution, perhaps of pre-initializing the model state before the auction. We are looking into various libraries, the environment that modern browsers offer, WebAssembly, and similar other techniques. Here our work is technical, and there's a lot of research we can do internally, but it is important to collaborate in these kinds of efforts with the browser providers, and that's what we are doing. If we are to find a way to optimize the model execution, this has to be done together in collaboration with browser vendors. There is going to be a question of fraud detection and prevention. As you may imagine, real-time bidding auction being done on the browser opens new fraud attack vectors. A malicious actor could try to tamper with our bidding code and fool us into paying more than we'd like to be paying for the impression of an ad. So these are novel attack vectors that we will have to research and mitigate or perhaps eliminate completely. There's also the problem of model and signal obfuscation. And here, the source of this problem is that some of the signals that we use might relate to financial or campaign configuration details of our clients. And we would still like to use these kinds of signals on the device, but at the same time, we have to make sure that these signals are not accessible to, for example, competing companies. But let's focus on machine learning prediction quality. This is the first problem that we faced. Of course, prediction quality is intimately related to the effectiveness of our reporting mechanism and to the optimization process. But what we first did was to try to make sure that the signal granularity and signal quality that's available on the device is optimal for the purpose of conducting the real-time auction. When you think of a technical shift like this, there's two levels of thinking about such a shift. So one of them is that you could try to take a look at the specification that's proposed by Chrome or other browser vendors that propose their solutions and try to design a system that is optimal for this particular specification. And another approach that you could take is to try to understand the privacy goals and other goals and restrictions that each browser vendor is working with and that each browser vendor is trying to satisfy, and try to think what would be the system that satisfies all those goals and at the same time is optimal from the perspective of an RTB auction. So this is what the latter approach is what we did at RTB House. We try to start with first principles and see what is the best solution that the entire ecosystem could deliver. Since the first draft was proposed by Google Chrome, we were very busy trying to come up with ways to improve this proposal, and through many months of discussions and design, we arrived at two major extensions to the initial Turtledove proposal. And these two extensions were warmly welcomed by the RTB community and are in fact now incorporated into the current iteration of the solution that Chrome is working on. There is no time to go into details of these two extensions or of these two proposals by RTB House. I encourage you to visit the W3C GitHub page that is linked on the slide if that's interesting to you, and those links contain the descriptions of the extensions that we proposed. So the bottom line of this slide is that RTB House is very active publicly through the discussions on the W3C forum and other public forums. We try to ensure that the RTB ecosystem is going to be optimal and is going to satisfy the requirements of a high quality RTB solution. Let's say it that way. So if we make sure that the environment and the signals available on the browser are satisfactory from the perspective of the model evaluation, the next thing that might come to our mind is what reporting capabilities we will have while conducting an RTB auction and all the necessary computation. So of course, in order to optimize our model, we will have to have some way of gathering statistics on the central server. And as I mentioned in the beginning, the environment that we are going to execute our code in is going to be sandboxed. What that means is buyer's JavaScript will have limited ways of contacting with the external world. Free network access is not going to be available, and so there has to be a dedicated API for submitting and aggregating statistics coming from single browser instances. This is in fact an area of discussion right now. Most browser vendors have proposed certain solutions that could satisfy this use case, and one of them is proposal coming from Google Chrome that can be summarized with a single picture coming from their repository. Of course, this is quite an advanced system, and we won't have time to describe it in detail. Two interesting aspects of this system is that first, this system operates with a certain mathematical framework to reason about the privacy guarantees that are going to be met. This is the framework of differential privacy. So we have a strict mathematical apparatus to reason about the privacy guarantees that each user will get. And moreover, the system leverages a certain computing paradigm called multi-party aggregation, which ensures that even if some of the helper servers taking part in this aggregation process gets compromised, there is no technical possibility of accessing the reports submitted by single browser instances. And of course, what the system does is that there is large number of browsers. Each browser might submit certain key value pairs, and those key value pairs are then going to be processed by a set of helper servers, which will then collaborate to give the buyer, whose code emitted the key value pairs in the first place, access to aggregates over those values. So in the end, the buyer may try to find out what is the sum of values for a certain key. And this service, or a similar service, is going to be the basis of the optimization process that we will apply in order to train our models. Here, the message would be, for this particular slide, at RTB House, we plan or we intend to be active in the discussions about these aggregate reporting mechanisms in a way similar, in a way which is similar to the one where we shaped the current solution for RTB auction, which is named FLEDGE, and we will try to make sure that the setting for aggregate reporting will be as optimal or as good as possible for us. And this brings me to the concluding challenge that I would like to talk about today, which is, after ensuring that the environment in which we evaluate our models is optimal and the reporting mechanism is optimal, what kinds of models can be trained effectively in this setting? How to optimize the execution time so that we don't have to overwhelm the user's device in order to carry out the auction? How to manage such a distributed system? And by managing the system, I mean deploying new iterations of models, handling all the available iterations that are currently deployed, how to monitor performance, and so on. So historically, we spent many years of research and development on our current models, and we expect to now do something similar, but this time in this new distributed system where the computations happen locally on the browser, and we will likely put a lot of effort into researching different kinds of models that can be created and optimized in this setting. So this concludes my presentation. I hope this was interesting to you. If you have any questions, I'd be happy to take them now. And of course, if these kinds of problems sound interesting to you, we are open to, we are hiring, and we'd be very happy to talk to you. Thank you for your attention.
Okay, Jonasz, thank you for your talk. We have a few questions from audiences. So starting with the first one. So what do you think about Brave browser approach to online ads?
Right, so not sure if I know that much about Brave, if this is the browser that I'm thinking about right now. If I am not mistaken, Brave is the browser that tries to cover all the ads that are presented on a web page and then display their own ads in the place of those slots. Please correct me if that's not right. Not sure if I can say anything interesting about this approach. Certainly, it has certain business not sure.
Okay, so we might move to the next question. So, how does the move away from the third-party cookies look behind the scenes? Do ad tech companies have to unconditionally follow what the browser vendor like Google says, or do they have some say in the future of the cookieless world?
We have been very active in shaping the solutions that are now on the table and that are actually now being deployed. Our experience is that Google and other companies are very open to the ideas that you might bring to the table as long as they are constructive. So if you are able to say, I'd like to achieve this and that, and this is how I'd like to do it, then they will be open to considering it, and they may actually eventually implement your ideas. In turn, if there is something that you'd like to achieve, but there is no technical way to attain that you can propose, and that's obvious perhaps, then your voice will likely not be taken seriously.
Okay, and also we have some time for the last one. So moving away from the third-party cookies surely represents challenges for retargeting campaigns. Will the situation be similar for branding prospecting campaigns, or maybe reaching new potentially interested audiences become more effective and easier thanks to this cohort approach?
The changes that I have described and that involve moving all the computations to the browser currently only apply to the retargeting campaigns. There is a good reason to apply some of these mechanisms to branding and prospecting campaigns as well, though this is not something that will be happening in the nearest future. And the second part of the question, will reaching new potentially interested audiences become more effective with a cohort approach? Retargeting will not be replaced by cohort approach. The retargeting solution works with a very strong signal about past user behavior, and this is the reason why it is so effective. So I expect that the retargeting solution will still be very strong, and we have to make sure that the technical approaches that we take to perform retargeting campaigns are as good as possible. And this is the focus of what RTB House is doing right now.